Hello everyone, welcome to Statics course. Today we are going to cover chapter 8.2, Problems Involving Dry Frictions. We have two learning goals. First thing is I want you to understand that characteristics of dry frictions, and we're gonna solve one problem with frictions today. So basically what I explained last time, so we have some pushing or pulling forces to the object, and obviously there will be some reactions. That is the frictional force, which is dry frictional force. And also we know that there is a weight of these boxes, and the normal forces. There is action and reaction. The weight and the reaction is the normal force of the object. The line of the action of the resultant normal force can be different depending on the we can calculate the moment at point O. So we can check where is the line of the action of the normal force from the center of the boxes. So here, this guy is pushing the, let's say this is the refrigerator, okay? So how many forces are associated with these situations? We have pushing forces, and the reaction is frictional force, which is opposite direction with the same amount of force. And also there is a weight from this refrigerator box. And we know that there is a reaction, that is the normal force, but the line of action can be differentiated from the line of the weight action. Okay, this is, we can say, the distance x. So we can apply two-dimensional equilibrium equation to solve this problem, since this box is stationary. Or it can be impending motions. It almost reach to begin to move. Okay, impending motion, or this one is in stationary. Yeah, that's the two cases. Once this object is in impending motions, then we can use the equations. What is that? The last equation is that we learned the static frictional force is equal to the frictional coefficient of the material times the normal force. So this is our fourth hidden equation to solve the unknown variables. Okay, so please remember that once the object is reached the impending motions, then the frictional force is it can be a maximum. Okay, so static frictional force is the maximum frictional force. Compare, it's relatively higher than the kinetic frictional force. Okay, now we are going to look at the new concept. Will this box slide or tip? Okay, what does it mean, the slide or tip? There are only two options. Okay, whether this one will slide, okay, this box will slide, or this box will tipping. Sorry, my bad drawing. Will this box will sliding or tipping? That's the two cases we have to think about. That's a totally different event. We can decide whether this one will slip or tipping. Okay, how? If this the horizontal distance x from the center of the boxes to the line of the normal forces, we call this is distance. Okay, this distance is less than this x is less than b over 2, then, or we can say that this box will slipping. How about the other case? This x is equal to b over 2, which means the normal force, the line of the normal force is located at the edge of the boxes. That means when we push certain amount of force, then because of the normal force are acting on the edges, this box will tipping. Okay, so we have an assumption. We have to make an assumption before we solve the problem. This box will slipping or this box will tipping. Okay, we can check using the equilibrium equation whether this box will actually slipping or actually tipping. We have to verify our assumptions based on the calculation. Again, so first thing first, let's assume, okay, when we solve the problem, we have to assume whether this one will slipping or tipping. If you assume this one will slip, this one will slipping, then you know that there is equilibrium, oh no, not this one. This one is frictional force, frictional equations. Friction equation means your frictional force is reached the maximum frictional force, which is static frictional force, which is mu s times normal force. If you can't understand this equation, please go back to the previous class lecture note, lecture video. There is an explanation. What is this? So we know that the frictional force is already a maximum. It's impending motion. It's impending slip. So the frictional force is the maximum, which is static frictional force. Then we can solve other three unknown variables, the distances and the pushing forces, pulling forces, normal forces, which one is three unknowns. Then usually the weight is known. Okay, so we can solve these three unknowns based on the equilibrium equation what we have. Then we can check whether this distance x is less than the half of the width, which is b over 2. So you have to check whether this equation is satisfied. Another option we have to think about that, okay, then let's assume this one will tipping. Tipping means we know that the location of the normal force is located at the edge of the boxes. So we know the distance should be equal to b over 2 from the center of the boxes. Then we can solve push force, normal force, and frictional force. Remember, this frictional force is not reached the maximum frictional force. Since this one is tipping, okay, so this equation must be satisfied. The frictional force should be less than equal the static frictional force, which is mu s times normal forces. Let's solve the one example so you guys have a better idea what I'm talking about. See, here we have a crate weight is a 250 pound force, okay? And we have a coefficient that is 0.4, okay, which is pretty high. The maximum force P, maximum force P that can be applied without causing movement of the crate. Okay, the question is find the maximum force P, without causing movement of the crate. So that means we have to find the force that can create static frictional force, which is impending motions. Okay, so here we have a certain plans. First, we have to draw the free body diagram and determine the unknowns and make your friction assumptions. We have to make an assumption whether this one will slipping or tipping. Then apply the equilibrium equation as well as the friction equation too. Okay, and check the assumption. Alright, then first one, let's assume that this one will sleeping. Okay, so sleeping means this one sleeping means our frictional force should be equal to mu s times normal forces, and the vertical distance, no, horizontal distance should be less than equal to b over 2, less than b over 2. Okay. Alright guys, let's solve this problem. Let me remove my keyboard. Sorry for the noisy sound. So let's draw the free body diagram first. Project. We have a pushing force. There's a distance. You know what? Actually, we know the weight W, which is 250 pound-force. We have pushing forces. There should be a frictional force, which is opposite direction, and there should be some normal forces, and there is a distance from the center. So how many unknowns we have here, 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 and here. But since this one we assume, then this one will sleeping. Okay, so let's apply the equilibrium equation. Sigma fx equals 0, sigma fy equals 0, sigma any point moment O should be equal to 0. Let's say this contact point is point O. For the x-axis direction, total orientation. For the x-axis, we know that, okay, there is pushing forces, and there is there is a frictional force, so it's equal to 0. So that means P is equal to F. How about the vertical forces? We have a negative 250 pound force plus normal force. This one should be equal to 0. So that means normal force is equal to 250 pound force. Alright. And we can calculate the moment at point O, here, point O. Then we know that the force P creates a clockwise rotation, so which means the sign should be minus. We don't know the P times 4.5 feet. And we have another force which is a weight. Weight creates a counterclockwise rotation, so the sign should be positive. 250 times x feet. This one should be equal to 0. Again, we already know the frictional force. Since this one is impending slipping, that means this F should be static frictional force, which means mu s times normal forces. Mu s, we already know that mu s is 0.4 and the normal force is 250 pound force. So in this case, frictional force is equal to 100 pound force. So P is equal to 100 pound force. If we plug this number to here, then we can find variable x is equal to 1.8 feet. Okay, so we have a distance x is 1.8 feet. But wait a minute, we have to check whether this distance is less than the half of the width, which is b over 2, that is 1.5. Since 1.8 is actually greater than 1.5, so that means this one is satisfied, this is not satisfied. Okay, this equation is not satisfied, so our assumption has some issues. Okay, it's wrong. So this object will not slip. This one will tipping. Okay, so let's check another way. So let's make an assumption. This one will tipping. So tipping means our frictional force is less than equal to mu s times normal forces. It can be reached the maximum static frictional force. It's possible, but it's relatively, usually it should be less than. So we have to check this one at the end. But we do know that since this one will tipping, that means our horizontal distance should be located at the edge of the boxes. So that means this one should be 1.5 feet. This is known, okay, based on our assumptions. So let's apply the equilibrium equation. Sigma fx equals 0, sigma fy equals 0, sigma moment any point O should be equal to 0. This point is O. So same thing, we can say that, okay, this is positive P minus F is equal to 0. For the vertical one, minus 250 pound force plus normal force equal to 0. So normal force is 250 pound force. P is F. Then we can calculate the moment, which is pushing force times 4.5 feet. This pushing force create clockwise rotation about point O, so sign is minus, and the other one is weight. The weight create positive moment. 250 times 1.5 feet. We know the perpendicular distance from the point O, so this one should be equal to 0. So from the last equation, we can find that the P is equal to around 83.3 pound force. So since our first equation tells us P is equal to frictional force, so frictional force is 83.3 pound force. Alright, let's check whether this one is less than equal to mu s 0.4 times normal force is 100. No, never mind. Normal force is 250, which means this one is what? This one is 100, right? So actually, this frictional force is less than equal to 100 pound force. So this is true. So we satisfied these conditions. So we can say that this pushing force, the maximum pushing force to create the movement, to create the motion of this crate is 83.3 pound force. This is the maximum force we can push, and we can say that the movement is tipping, not slipping. Okay? So you can check the detailed answers in the PPT slide. Okay? You will check the answers. Here we have that. Okay, the frictional force what we calculated is less than equal to mu s times normal force, which is static frictional force. That means we have a tipping occurred. So we satisfied these equations. All right, just wrap up quizzes. The first question is, friction force always acts blank to the contact surface. What's your answer? Friction force always acts to the contact surface? Is it normal at 45 degrees, parallel, at the angle of the static friction? It should be the parallel. Okay, friction force always acts parallel to the contact surface. And if a block is stationary, so it does not move, then the friction force acting on less than equal to mu times normal forces, or is equal to what is the mu k? This is kinetic frictional coefficient. Okay, greater than equal to mu s. So what's the question? What is your answer? If the block is a stationary, that means this one is possible, but it's still in impending motions, and this one is more right answers, less than equal to mu s times normal forces. So the answer should be A. Today we learned some characteristics of dry frictions. It can be slipping or tipping, and you have to check your assumptions based on the equations. For the slipping, you have to check the distance should be less than half of the width. The tipping, you have to check your frictional force. It should be less than equal to mu s times normal forces. So this is the key things. Alright, thanks for watching this short video. Have a great day.